3 this week. Part 1 of experiment 3 is what we are going to be doing, so I'll talk to you about that in a little bit. You'll have your quiz this week, quiz number 3. Make sure you bring calculators for the quiz, but always bring calculators for the quiz. Discuss, and for other calculations in lab, you'll be having a discussion of the conclusion for your experiment 1 report in lab. And then your experiment 2, your molecular modeling answer sheets are due in lab this week. It'll be collected at the start of the lab period. So the lab that you did last week, those answer sheets plus the printout of your morphine model once you were done with it are all due in lab next week, or sorry, in lab this week. Okay, so experiment 2 is due this week. Next week we will finish experiment 3. So we'll do experiment 3 part 2. And then your experiment 1 report will also be due in your notebook next week. So we'll be taking your notebooks from you next week. Okay, so make sure when you come to lab next week you have your report all ready to go. So this week for experiment 3, we're going to be taking nutmeg. So it's going to kind of smell like cooking class in the lab. And a lot of nutmeg, so much more than you would ever use. We're going to extract out trimyricin, which is in the nutmeg, and then we'll kind of end at that point this week, and then next week we will take that trimyricin and convert it to myristic acid. Okay? So first of all, a little bit about trimyricin. It is a fat. About 20% of nutmeg is this fat. Okay, so there's other things in nutmeg besides just the fat. And this is calculated. We'll calculate it by mass. Okay, so we won't do mole ratios or anything like that. But when we do our extraction yield, about 20% is what should come out of the nutmeg, whether or not that's how much we get, okay? And so this fat looks like this. Has kind of the same basic structure of most fats. Triester. So all three of these guys, 3 of these chains are all linked together. So drawn like this, it looks like it's a really compact molecule, but keep in mind here we've got 12 CH2s in here. So a really long chain attached to these esters, and they're all attached to each other. We've got the 3 of them attached to each other. It is very soluble in ethyl ether. So we'll talk about how we'll use that. And ethyl ether is a relatively low polar solvent. Has low polarity, as does this compound. So we do have the ester groups, but with these really long chains coming off of it, it's a really low polarity compound, okay? So you need something that, remember from Gen Chem, like dissolves in like. So that's why we want to use the ethyl ether, which is very similar to this compound as far as polarity. It is not very soluble in methanol, so we will also use that. So when you think of ether versus methanol, the methanol is a higher polarity solvent. So that's why with just the CH3 OH group, it's much more polar than the ethyl ether. And so we talk about this. This is a homo triester because each of these chains are the same thing. So they're all the same esters being linked together. and it's a homotriester of glycerol. So this part is the part that's related to the glycerol. And we'll talk more about that next week when we look at the hydrolysis. But most fats are triesters of glycerol. Okay, so there's a little bit of introduction to our friend trimeristin. Now, one thing I want to show you in getting ready for this experiment, let's look at the pre-lab that is in your lab manual, okay? So you kind of pretty much have a pre-lab that you can use or base your pre-lab off of for your experiment this week. And so remember, even though we're doing part 1 of this experiment, when you come to lab this week, you want the entire pre-lab in your lab notebook, as you should each time you start a new experiment. You want the entire pre-lab in your notebook, all right? So I won't read through all of the pre-lab, but I want to kind of point out a few differences versus what we looked at with experiment 1. And then also there's some things that you need to add to this and make some corrections to this so that it is correct for putting into your lab notebook, all right? So purpose of the experiment is okay. Then the next part, and title is okay, the next part is where we would show our balanced reactions that are taking place in our experiment. Well, for the first part of the experiment, all we are doing is stirring the nutmeg in ethyl ether and extracting out the trimeristin. So there's no reaction that's taking place, okay? That is more a workup step. And so that is not shown as a reaction. That is shown in the flow chart, okay? So you've got your nutmeg, and you're extracting it with ethyl ether, and you'll get trimeristin and a lot of other things besides the trimeristin and diethyl ether, and then you'll have solid nutmeg residue that you filter away. So you'll do a filtration here, a gravity filtration, so we'll talk about what that means, to separate these two. Then you'll go through, we're going to remove the ether, and we'll talk about why in a little bit. We'll remove most of the ether with simple distillation, so we'll have ether that is removed, and then we'll still have this chunk here, this trimeristin, soluble organic components, and a little bit of diethyl ether. We're going to add methanol to it. That will precipitate out our trimeristin. So we'll filter and get our trimeristin as a solid, and then our filtrate will have methanol and soluble organic components and diethyl ether in it, okay? So that whole process of how we get to actually having solid trimeristin, we're not going to show any reaction for that, okay? So does everybody understand why there's no reaction to show? The trimeristin is never changed into anything else. We're just taking it away from the nutmeg, all right? Okay, so the second part of the experiment, and the part that we will do next week, does involve a reaction, and there are 2 of them. We will hydrolyze our trimeristin using sodium hydroxide, and we will talk about the stoichiometry of this reaction next week, okay? So that's one thing that's really key to this, but this stoichiometry is correct. So over the week, see if you can figure out what is going on here as to why we have 1 trimeristin to every 3 sodium hydroxide molecules, and then from here on out we carry the 3 through when we convert it to glycerol and sodium myristate, and then the sodium myristate is then converted to myristic acid. There's always 1 trimeristin to 3 to 3 to 3 to 3 to 3 to 3, okay, at the end. So in the end next week, what you will isolate is that myristic acid. So you do need to show both of these reactions, because these are both reactions that will not be shown in the flow diagram, all right? So it's a little bit different than experiment 1, where our reactions also showed up in our flow diagram. What we're going to do for this flow diagram, and we'll talk a little bit more about it next week, is show what happens after that reaction, okay? So we've got all our pieces here, we add the HCl. We're going to then, after the HCl is added, do a filtration to isolate our myristic acid and then all of the other impurities, including the glycerol and ethanol and water and sodium hydroxide and or sodium chloride and HCl. And then we go on to do a recrystallization where and this piece here is just to show you that this is glycerol, okay? So this isn't an extra step. Then we go on to recrystallize this, and once we recrystallize, we'll filter and get our pure myristic acid and then all of the other stuff, the methanol and all the other impurities that came out of it, okay, and water. So make sure that you understand the difference between these two sets of procedures and why we don't have a reaction for part 1, we just have a flow diagram. For part 2, we have reactions to show and the flow diagram to show to get to the end, all right? The other parts of the pre-lab, you've got your table of reagents as well as products, so you want to make sure that that completely takes care of all the chemicals that are going to be used or produced in your experiment, so kind of double check your table, make sure that that is all taken care of. We've talked about the flow diagrams, so then things you need to add. There isn't any drawing of new special equipment, so 2 things that you will use are a reflux apparatus in part 2, and you will use gravity filtration in part 1. So you want to make sure you show both of those. And then also make sure you update what edition of, update this reference, okay? We don't list Dr. Mungle anymore on it, it's edited by me, and update the year on there, okay? And then the last part I wanted to point out to you, and in general with the pre-lab, so we've given you a lot of information for helping you put your pre-lab together. Pretty much you have your pieces and you need to put your pieces together. Make sure whenever you're putting stuff in your notebook you understand where it's coming from, okay? So make sure that you understand what the reactions are. You understand why that table of reagents looks like it does. You understand the flow diagrams and understand this yield calculation, okay? By you putting it in your notebook this week, any of this potentially could be free game as far as a quiz, okay? So make sure that you understand where those pieces are coming from, all right? So I'm going to talk about the specifics with the process as far as our extraction this week, but also want to talk to you about, in general, the kind of categories of what we're doing in general as far as chemistry. So the use of nutmeg to get to trimyricin then isolate the trimyricin is an example of an isolation of a natural product, okay? So we took something that when we're talking about natural products, we're talking about things that come either from plant material or animal material, and we're isolating something from that, okay? So we took the nutmeg, which is a plant, and we're isolating something from that nutmeg, all right? Now, in terms of organic chemistry, usually when you're looking at something that is a natural product, you then would want to, we would want to go, okay, we've isolated this trimyricin, now what could we use it for, either pharmaceutical industry or some other industry? What would we then take on this natural product to do something better for us, okay? We're not going to then take on the trimyricin and see, you know, what it tests for biological activity or something like that to be used for a pharmaceutical. So we're isolating this natural product, but beyond that, it's not necessarily a natural product synthesis or anything like that, okay? But related to this, how this relates to things that happen in organic chemistry is a lot of things that we use, things that make us feel better as far as medicines, come from things that were derived from natural products, okay? So like about half of FDA approved drugs right now come somehow from origins of natural products. And so whether it was the original natural product or they learned something about, a lot of times these natural products have pretty complex structures. This guy isn't too bad, but I'll show you one here in a minute. They have fairly complex structures. So then people learn more about how that structure is important into the function of what it does, and can that structure be important in doing something else for another use, okay? So a lot of our pharmaceuticals still come from things that we learn from natural products, whether plants or animals. Another example of something that is a natural product is caffeine, right? We extract, either you're drinking coffee or you're drinking tea, those are both examples of extractions, right? You're extracting from a solid to get something in a liquid solution, and part of what you get out of that is caffeine. We also just extract just pure, caffeine to put into like soda comes from an extraction process, okay? So this is an example of, and then it's also been synthetically made, but this is an example of a natural product, all right? So the one I'm going to show you here, Taxol, this was one that was kind of like the premier, one of the premier compounds for learning something new for the pharmaceutical industry as far as getting something that was really useful as a medicine, and then trying to learn a lot from its synthesis and how this compound is put together. So let me show you what it looks like, because it's a really complex looking molecule. There's been many groups, research groups, looking at it around the world, around the country and around the world, to try and synthesize this guy. So as you guys learn more about organic chemistry, you'll learn that all of these places where we have wedges and dashes are chiral centers in this compound. So that when you look at something that has all of these, when you look at a compound that has a number of chiral centers, that usually means it is really hard to make, okay? Because you have to make these and then make them stay and not change, okay, in the process. So this is a really complex compound. Well, it's also a really important compound because it's used as a cancer drug for breast, ovarian, and lung cancer. It comes from the Pacific yew tree. And the problem with it coming from the Pacific yew tree is it comes from its bark, okay? So as soon as you go and try and extract the Taxol out of the tree's bark, by pulling the bark off the tree, you're going to kill the tree, right? As with any tree, it needs its bark. You pull its protective covering off, it's going to die. So that's not really a sustainable method for getting something that is such an important pharmaceutical agent, okay? The other thing is Pacific yew trees are not like, all over the United States. They're only in one region of the U.S. along the Pacific coast, and they grow really slowly. So they're not going to, you can't just go plant yourself a farm of Pacific yew trees and be able to extract all the Taxol out you need, okay? So this was found to be a really important drug, but chemists had to figure out how to come up with a synthesis for it. And so over the years, there's been multiple proposals of syntheses. And now what is used to make it is they basically use other similarly related compounds that can be extracted and then chemically transform them into Taxol, okay? But a person that would go through this process is a natural product chemist, okay? And so they're not just extracting, they're not just, going out into nature and taking things and extracting things out. There's a process that they have to go through to figure out if they're finding something that is really useful or not. So first of all, the first part is they have to extract. But then they have to screen what they extract out of the natural product, or screen that extract. And if they find something that looks useful in their screening, then they're going to separate it and then identify what is the important compound in this whole extraction muck that I have. And potentially, if it's not something that's really widely available, then you'd go on and figure out how to synthesize that compound, as they had to do with Taxol. Okay? Another example of pharmaceutical that came from natural product is there's a diabetes drug for type 2 diabetes, Byetta. It comes from the spit of a Gila monster. So they found that Gila monster, in its spit, is this compound. And it's a big macromolecule. It's a big 39 residue peptide. Okay. And so it's got 39 amino acids and ends in an amide. But they found the compound in a Gila monster, and it worked for treating diabetes. So then they had to go on and figure out how to make it, because again, trying to get the Gila monster to like spit enough to then extract enough of it out to have enough to be a sustainable drug. They had to go on and figure out, well, how do we actually make that? So they have it. Went on the market in 2007, 2008, and still is on the market. But other examples of things that have come from natural products, like your car tires. Originally, car tires were made out of natural rubber from a rubber tree, okay? Or any rubber that's used, it came from a rubber tree. So that's another use of a natural product. So it's not just pharmaceuticals that these natural products go on to help improve people's lives, okay? But this is what we are doing this week, is extracting the natural product, then we're going on and using it for synthesis, but we're not necessarily going on and testing the trimeristin itself for other uses. So, to isolate our trimeristin, turn this off for a second here. We're going to use what is called a solid liquid extraction. So what would this be related to? What have we already done? We've already done a liquid-liquid extraction, right? The first week of experiment 1. So now we're just going to get rid of one of the liquids and put in a solid, okay? So a solid liquid extraction, you're going to have a solid, and you're going to have a liquid. Okay, so our solid is our nutmeg, our liquid is our ether, all right? Now there's a couple things that we need to keep in mind with this solid liquid extraction. The first thing I'm going to do is talk about diethyl ether. There's some things we need to think about when we are using diethyl ether, okay? And first of all, diethyl ether is also known as ether. It's also known as this. So there's lots of, you could get rid of the dye too, ethyl ether. These are all the same thing as far as what we're talking about in the organic lab, okay? The thing with the diethyl ether is extremely volatile. Has anyone done their pre-lab yet? What does it boil at? 35, 36, 34 degrees, really low, okay? So about 35 degrees. So room temperature is low 20s to 25 degrees. It boils at 35 degrees Celsius. It doesn't take a whole lot to get it to boil and vaporize. So it evaporates really quickly on you, so you have to be careful of that. So we're going to talk about precautions we'll take because of that. The other thing is it is super flammable. Okay? It very easily can be ignited just by heat. Like, it doesn't need a spark. It doesn't need a flame nearby. Just the presence of heat could cause the ether to be on fire, okay? So we need to take precautions whenever we use ether. We don't want to have, like a container of ether. We don't want to heat it directly on a heat plate. Just the vapors coming out of it could catch on fire once they had contact with the heat plate. We've got to be careful, obviously no flames around it, no sparks around it, things like that. So be really careful with the flammability of ether in general whenever you are using it, as you should with any organic solvent, but ether's probably the most volatile of the ones that we'll use, okay? The other thing is because of its volatility, it does want to evaporate on you really easily, okay? And so we're going to be using saran wrap this week to help prevent a problem with that. So we're going to cover, you're going to be using an Erlenmeyer flask when you're stirring your nutmeg and your ether. You want to cover the Erlenmeyer flask with saran wrap, and so there's saran wrap in the lab. And then when filtering, you want to cover the funnel and flask, cover as much of the openings as possible. Funnel and filter paper with saran wrap. Keep it so the ether won't evaporate. Because if it evaporates, what happens is when we're filtering, it's going to get trapped in the solid nutmeg and precipitate out with the solid nutmeg instead of going through with the filtrate. And we want to keep it in the ether filtrate, okay? So you got to be really careful to keep everything covered in saran wrap, and when you're filtering, keep everything covered in saran wrap so it doesn't evaporate on you, all right? So when we go to filter our nutmeg, we're going to be using gravity filtration. So a few of you had to use gravity filtration in experiment 1. All of you will get to use gravity filtration in experiment 3. We don't need the towel around our flask though, because we're doing things at room temperature. It won't be heated, okay? So with gravity filtration, what you guys are going to learn this week is you'll have to learn how to flute filter paper, okay? So that's a new technique for you, is fluting filter paper, which is very useful to learn how to do it well, okay? There's multiple times that you'll be using it in lab, and it can kind of be therapeutic too. You're basically folding paper. It's kind of like organic origami. But you want to do a really good job at it so your filtering doesn't take too long, okay? So if you do a good job, things will filter well. If you don't do a good job, things don't filter so well. So learn how to do the origami well. But when you're covering things, you're going to want all of this covered while you're filtering, all right? And if you start seeing kind of an off-white solid crashing out on your nutmeg, that's your trimeristin. And so what we'll have to do is everybody's going to start with 2 extractions. So you're going to stir your nutmeg in the ether, filter it with gravity filtration, put the nutmeg back in another round of ether, stir it, filter it with gravity filtration. After the second filtration, if you see yellow or off-white solid in with your nutmeg, we've probably lost some trimeristin, so we'll have to decide if we have to do a third extraction or if we can use some rinses to help get all that trimeristin into your nutmeg, okay? Because you want as much trimeristin as possible from your nutmeg so that you're good to go, you have enough material for next week, all right? So after your 2 extractions, if you have questions about what trimeristin is being left behind, make sure you talk to your lab prof and see if you need to do more extractions. It's easier to take care of it now than in the end of lab find out you don't have very much stuff and then we've got to go through the process again, all right? Okay. So what you want for next week this week, when you're done collecting your trimeristin, you want about, something that would be nice would be about 1.5 grams or so of wet trimeristin, solvent wet. So when I talk about wet, not water wet, solvent wet. So you want something in that ballpark to make sure that once it dries next week, we want to start with about 1 gram dry, all right? So things that we're going to do for the extraction to help things work in our favor. The extraction itself depends on, first of all, the solubility of what we're trying to extract out, okay? So our trimeristin is really soluble in the ether, so that's good, but also with that solubility is the volume of solvent used, okay? So since it's really soluble, we're not gonna have to go through tons of solvent, which is something that we want, all right? We're going to extract it multiple times, okay? So the number of times the solid is extracted is important, okay? So we will start with 2 by 30 mils or so. We're extracting things twice. This is better than if you just did it once with 1 time 60 mils. So you're using the same volume of solvent, but actually going through the extraction multiple times helps you get more of what you're trying to extract out of that solid, okay? So whenever you're doing an extraction like this, you would always want to do things more than once, all right? Particle size is something else that's important. So we're not using, like nutmeg is actually a nut, kind of like an acorn nut. We're not going to, take solid nutmeg nuts and put them into our, take the solid, quarter size or so and put it into the ether. That's not going to help us get much nutmeg out, right? So we're going to use powdered nutmeg, which is much better than just the solid or non-powdered nutmeg, okay? The other thing with particle size, you could also call this making sure you have good contact, okay? So by having a smaller particle size, we've got good contact of the powdered nutmeg with the ether. You want the ether and the nutmeg coming together really often and coming together well to make the extraction work, all right? The other thing that's important is make sure you have good stirring. So besides our solubility, number of times we're extracting, our contact or making the particle size the right particle size, and with the contact like that, if you're looking at liquid extraction instead of particle size. That's why you shook your separatory funnel, just so that you got good contact of the two layers. We're going to have good stirring. So you want to make sure you clamp your Erlenmeyer flask, because you're going to need to have really good stirring in that flask to make sure you get all that extraction, all that trimeristin extracted out, okay? So we want to have high stirring, and we don't want the Erlenmeyer flask just walking off the hot plate, all right? So once we go through this extraction, then what we're going to do is we're going to partially distill the ether, okay, using simple distillation. Well, this partial distillation is what's called a concentration. We're not going to remove absolutely all of the ether, but we're going to remove part of it, okay? And we're going to get down to about 15 milliliters of ether, okay? And so with that concentration, we're removing the solvent that is really soluble in, because now the next step is we need to get that trimeristin out in some fashion as a solid, and we're going to precipitate it out with the methanol. So if we leave the ether in and just add methanol to it, we're not going to get as much solid out as removing most of the ether and then adding the methanol to it. Now the reason that we leave just a little bit of ether is there's other stuff in there besides just the trimeristin that came out of the nutmeg. So we want the junk to stay in the ether, okay, and end up, and then there'll be ether methanol mixture, and end up having just trimeristin comes out of the methanol, okay? So we do this concentration first to remove the solvent that makes it, that it's very soluble in, and then we're going to precipitate with the methanol, which it is not very soluble in. Okay, and when you add the methanol, make sure it has cooled down to room temperature, so you don't want to have like hot ether trying to add then another flammable solvent on top of it. Let everything cool down to room temperature, then add the methanol, then stir it for a little bit. Sometimes the trimeristin takes a little bit to crash out. It may even be a good idea to put, if you're not seeing a lot of trimeristin, put your flask into a cold water bath with a little bit of ice and try and see if the cold will help precipitate out the trimeristin. But don't try and, if you don't have a lot of solid crashing out, don't just immediately go on to filtration. Try and get that solid to form, okay? Then once you've precipitated with the methanol, this time we're going to filter with vacuum filtration. And you're going to rinse the solid with a 1:3 ratio of solvent that is ether to methanol, okay? And make sure you cool this down in an ice bath as well, all right? So you want 1:3 ether to methanol rinse for rinsing that solid. Rinse out the flask that the solid came out of, and then rinse the solid itself when you filter it, okay? And then as far as the solid, you just want to make sure that you put it away in your drawer such that it's going to dry really well until next week, all right? So we want all that ether to dry off, because what we do need is we need to calculate the yield of trimeristin that you got, all right? And we need to know how much trimeristin you're going to be using for next week, okay? So since we're drying in between, one thing we don't have to calculate, and your lab manual will tell you you need to do this, but we don't have to calculate the percent loss on drying. And what we would be calculating is the percent of solvent loss after we let it dry over time. So what we would have done is taken a small sample, set it aside, let it dry, and see how much weight it lost over time, and then gone through and carried on with the rest of the trimeristin to make the muriatic acid. This year we've divided things into 2 weeks, and so over the week things will dry. We're not going to have to calculate how much is lost on it drying, because next week you want to take the weight of your dry trimeristin, and you'll know exactly how much your dry trimeristin weighs. Okay, so make sure you get the mass next week of dry trimeristin. The other thing you will want to do is set aside about 0.05 to, depending on how much you have, to 0.1 grams. We need that for calculating melting points at the end of the experiment. Okay? So you need the mass of all of the dry trimeristin, and then we need to set aside about 0.5 to 0.1 grams for calculating the melting points. All right? Now, one yield calculation that you are going to do for the trimeristin is you actually need to calculate an extraction yield. So we're not going to do a regular theoretical yield calculation for the trimeristin. You will do that for your muriatic acid. But we need to figure out our extraction yield for how much trimeristin you recovered versus how much nutmeg you started with. Okay? So we're going to divide by our total grams of nutmeg, and we're dividing our grams of trimeristin by this number. And then we want a percentage, so we'll multiply by 100 to get that as a percentage. Okay? So beyond knowing how much trimeristin you're using for next week, which it's really important to know how much trimeristin you use for the second part, you also need to calculate this as extraction yield. All right? Okay, couple things for cleaning up this week. There is a nutmeg waste container in the reagent hood. This is only for solid nutmeg, okay? So, no, don't add any extra solvent. Don't add any extra water. We just want your solid nutmeg. After you've completed the extractions, let things dry out a little bit, you'll be able to scrape your solid nutmeg into the waste container, okay? So the solid nutmeg from your filter paper, the solid nutmeg that's left in your flask goes in this container. But don't try and rinse it with anything into the container. The whole point of this container is what is contained in here is actually going to go in the garbage. We just need to let the ether fumes come off of the nutmeg, and then we can throw it away, because it's just like if we were cooking and we had too much nutmeg, we'd throw it in the garbage. Okay? So no solvent, no water in here. Otherwise, that prevents us from being able to dry out the nutmeg really easily and be able to throw it in the garbage really easily. Okay? The other thing, this experiment is really notorious for getting stuff everywhere on the balances. So clean the balances as you're using them, okay? If the nutmeg spills out on the balance, we still don't want solids all over the balances. So sweep up the balances, keep them clean, get all the nutmeg swept up around the area that you are weighing things out, as well as the area that you're working in, okay? Any questions you guys have? All right. On
the pre-lab, so since we already drew in the distilling apparatus from the first lab, do we have to go again?
No, this is only new equipment, so that's why you just need to show the reflux apparatus and the gravity filtration, but you don't have to use the simple distillation. Now what you want to do in your write-up as you're writing your experimental for experiment 3, still when you do the simple distillation, refer back to that page of your pre-lab of experiment 1, saying that it was set up like page so-and-so, okay?